Recall that axioms are statements we take to be true without proof. In the previous section, we discussed the field axioms and the order axioms. Both Q and R satisfy both sets of axioms. In this section, we're going to introduce the axiom that separates the two, which is really where the subject of real analysis begins. Definition: a non-empty set S of real numbers is bounded above if there exists a real number m such that S is less than or equal to m for all little s in capital S. The number m is called an upper bound of the set S. For example, if S is the closed interval from 0 to 1, then m equals 2 is an upper bound because no matter which value of S you choose in the interval from 0 to 1, it will always be less than 2. The natural numbers is a set that does not have an upper bound because no matter what value of m you pick, there will always be natural numbers bigger than it. The sets that we work with don't have to be neatly defined sets like intervals and isolated points. They can involve infinite sequences of points, combinations of multiple intervals, and even more complicated fractal sets. At this point, we only care about whether upper bounds exist. There are a couple observations that we can make about upper bounds. If m is an upper bound of the set S, then any number m prime that's larger than m will also be an upper bound. This is intuitively obvious, and the proof is so simple that we're not even going to spend any time talking about it. A value smaller than m may or may not be an upper bound, depending on how far over you go. Intuitively, it seems there should come a point where you simply can't get any smaller while still being an upper bound. This value is known as the least upper bound, and is the smallest of all upper bounds. We denote the least upper bound of a set as sup S, where sup is short for supremum, which is an older Latin word that was used to denote the same concept. But the intuition that this value should exist turns out to be false for the rational numbers. There are very peculiar gaps in the rational numbers, such as at the square root of 2, where things go wrong. We will explore this idea in class. If we want to fill those gaps so that every set that has an upper bound is guaranteed to have a least upper bound, we need to use an axiom known as the completeness axiom. The completeness axiom. Every non-empty subset S of the real numbers that is bounded above has a least upper bound. Since this is an axiom, there is no proof. Students often find this confusing at first, especially when you combine it with the fact that this is an existence statement that does not even give you any insight about what that value is or how you might find it. Do you have a set that's bounded above? Then it has a supremum. In most proofs involving the supremum of a set, you will be using one or more of the following properties. Suppose m is the sup of S. If little s is in capital S, then S is less than or equal to m. If m prime is an upper bound of S, then capital M is less than or equal to m prime. If little m is less than capital M, then m is not an upper bound of S, so that there exists a little s in S such that S is greater than m. There is an analogous concept for a lower bound of a set, and the greatest lower bound of a set, which is known as the infimum. We do not need another axiom to guarantee the existence of a greatest lower bound of a set. If we assume the completeness axiom, it turns out that we automatically get the greatest lower bounds. We will talk about the proof in class.